Today's the 18 2, and this is 12:30 to 1:45. Okie dokie. Hello, Amina. Hello, Louisa, Ellie, Penelope, Alicia. Hello, Lola, Feeny, Chelsea, Bella. Hello, Aiden and Alex. That is great. Just a few more, and we got everybody. Hello, Anne Sophie. Hello, Errol. This is dynamite. Just missing 2. So let's see, who would that be? I'm missing Antonine and somebody. Okay. Good. Folks, let's go ahead and start up. So, first off, as usual, there's Antonine. First off, let's see if you have some questions. So, let me know what you're working on and if you need some help. So, type in a page, type in a problem. Let's get started. Let's get started. So, what's on your mind? Do you have any stuff in chapter? Probably you're working on chapter 3 still, because I just gave you chapter 4, because we've now finished talking about chapter 4. Anything in chapter 3, thermo, that you'd like to talk about? But I'll go either way. If you're into 4, let me know if you got a question in 4 or back in 2. So bear in mind, I will grade your books eventually once I see you, but I can't do it until then. So they will be graded like 30 points a chapter as per usual. So please do them. Keep up with doing them. But I can't grade it right now. So right now I'm just grading that you're there, and I'm grading online quizzes, which we'll have a second one here this semester next week. Okay, still waiting. Any questions from you about how to do some problems? Okay, and as I understand it, next Thursday we cannot meet because there's a teacher Fortbildung, a in-service day, if I understand that right. So we'll meet Monday and Wednesday next week. Okie dokie. All right, going once, going twice, going 3 times, going 4 times. No. Sorry yesterday about the pixelness at school. I hope it's better now that we're back in my basement. They told me to try Mr. Lee's room, and it was terrible. So if I do go back to school or have to show you something there, I'll do it in W201, which I think was at least okay when we had it there last time. It was certainly better than we had with our miserable day yesterday. So I'm so sorry. And if there's anything you didn't understand, please ask me. Okay? I tried to cover it in the order that Cheryl does in the book for the last section of chapter 4 on common ion effect and so on. But ask me if there's something that you didn't get because of the awful pixelness. Okay, then let's go ahead and start up with a new chapter, new ideas. Okay, we have 2 chapters on acids and bases. I hope I can get you back sometime where we could do some labs on them. All right, if not, we'll have to do them as demos at school. But for now, let's talk about chapter 5, acids and bases. Some of you had this with me in ninth grade, acids and bases. That will be a helpful start for you, okay? A helpful start. But we're going to go way, 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 way beyond what happened in ninth grade. But at least it's a place to begin. So let's see what you know. Let's talk about the Arrhenius definition of acids and bases. We didn't call it that in ninth grade, but that's who it was. It's a Swedish guy, if I can spell his name right. Arrhenius definition. Definitions. Okay, you ready? Acids contain and bases contain So can you fill in the blanks so I know you're out there this morning, this afternoon? So what do they contain? Acids contain what in their little formulas? Or in their molecules, I should say. They have what in their molecule, and bases have what in their molecule, okay? What's the basis of bases? And what's in an acid? There goes my pen. To parts unknown. I think it went to the Philippines this time. I don't know where it's gone to. Maybe to Namibia or South Carolina. There it is. Super, good. Thank you, Aiden. They contain a hydroxyl group. So let's make that an OH minus. And I know we called it, Aiden, a hydroxyl group in 10th grade chemistry. Here we're going to call it just a hydroxide, okay? So we'll call it for the name of the ion. Dynamite. And acids, as Anne-Sophie knew and others as well, contain an H+. Notice I didn't say an H because it really is an H+. And if you think about it, an H+, and this is weird, it's a proton. Remember, hydrogens generally don't have neutrons, or rarely. So what that means is if it loses its only electron, it's all alone in the world. It's just a proton. So that's kind of weird. It's just a root with a positive charge. That's an H+. Bizarre, huh? But that's kind of what's going on. Thank you. A lot of you knew both of those. Super. Good. Chelsea, Alicia, and Mina. Okay. Let's talk about then the definition that is a little wider of what acids and bases are. And this is called, it's named after two people, Bronsted and Lowry, from, I think, England and Denmark. So where did that blue go? There it is. So the Bronsted-Lowry, how does she do it? She does ED. Definitions are different. Although the acid one is not so different to me. Let's see what you think. So acids can donate a proton. Well, now you know that's an H+, so that's not so different, is it? They can donate a proton. Bases can accept a proton. Or an H+. So that's a bit different. Bases are looked at differently than you might have thought of before. So up here, for example, for the Arrhenius, we can just say what? HCl, we know that's an acid. Or we could say NaOH, we know that's a base. It's got an OH minus. But for down below, we're going to do this on the next time I have the board free. And it has more to do with what they can do when they react with somebody else. Okay? So this is the old definition. It still works a lot of the time, but the new definition is going to work, well, right now. Here we go. Let's start up with that up at the top of the board. Let's take this SO3 minus, no, 2 minus, plus HF forms what? Okay, so here's the scoop when you get something like this. You got to look at it and say, well, I don't know. This guy can certainly donate an H plus because it's got one, right? Or a proton. And so if I donate the H plus, what is left? By the way, these are all going to be aqueous, but I'm not going to write it to keep it a little cleaner. Aqueous, 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 aqueous. So if I donate the H plus, what will be left out of HF? And don't say F. See if somebody can type it in and that it gets over the airwaves to me. You take off the H plus, what's left? Hey, thank you. Got a couple already. Got it. Super. Thank you, Chelsea, Alicia. It is indeed an F minus, right? So think of charge. Take an F plus off and the minus is left. Why? Because it started out as neutral. Take the plus and the minus remains. And it makes sense anyway. That's an ion you know, isn't it? Now what do I get here? Now take the H plus, attach it onto here. So I'm going to get H SO3 with what charge now? With what charge? Thanks to others for participating too. Amina, Anne-Sophie, Louisa, Lola. Okay, what charge will be on this now? See if you can figure this out. Good. Righto. I'm adding an H plus, so it is indeed just a minus or 1 minus. Why? Because if I add a plus to 2 minus, I get 1 minus or just minus. Yeah? Does it always work that way? Yep. Let's do another special one. Special one. Let's take a strong acid, HCl, and we're going to add water. Old liquid water. And do the same thing. Well, I don't have any choice. This guy's going to give its H plus, so I've got Cl minus left. Importantly, though, is what happens to the H plus. It attaches to here, and I get this guy, don't I? H3O plus. If I add an H plus to water, I get another H, and I get that extra positive kick that the H plus brings. It doesn't mean the O is plus. It means the whole molecule is lacking 1 electron, okay? We know this fellow. What's this special thing called? What's that special thing called? So a quick ion quiz. H3O plus is... Thank you, Lola. Thank you, Alicia. Is hydronium. And I got to tell you the truth. That's the way that H pluses really exist in water. They grab onto waters. So hydronium is just an H plus attached to a water. That's really all it is. But that's what we find in nature, okay? So in strong acids, we got lots of these hydroniums, okay? So strong acid solutions, sorry, so with water. So if someone asks you for the H3O plus concentration, it's the same as the H plus concentration, okay? I will use the two back and forth. Cheryl probably would kick me in the high den for that, but so H plus is for Mr. W also H plus. So the hydronium is also what I'm going to call H plus, okay? And I'm going to say that's in moles per liter to think of it as a number. So the amount of hydronium is really the same for me as the amount of H plus. Okie dokie? We'll get to numbers in a little while. Huge. Just pausing if I got any questions. Thanks, everybody, for chiming in. A lot of you knew hydronium. That's good. That's reassuring. I like it. Let's use these at the top. We're going to pick out some conjugate acid-base pairs. Conjugate acid-base pairs. Here's what I mean. HF, well, that's an acid, so I'm going to mark that as an A. And F minus is its pair. That's going to be its conjugate base. And I'm going to say it in words down below. Okay, so HF is an acid. F minus is called the conjugate. It's like the connected version of it. Okay, is the conjugate base. And it's always one is on one side, one is on the other. Look at the other one. Well, look at this. This is acting like a base now, right? Because it accepted H plus, so I'm going to put a B here. But its acid, ironically, is this. It's just got one H plus that it can give away. So these two are a conjugate pair. So let's put a little line between them. Boop. Conjugate pair. I'll abbreviate conjugate. And the two ones in blue are a conjugate pair. Conjugate pair. Do you always get two pairs? Yes. You always, if you have an exchange of a proton, somebody giving, somebody taking a proton, then you got two sets of conjugate pairs. Boom, 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 boom. And that's going to be an AP multiple choice question pretty much every year. So if you can identify the conjugate pairs, good on ya. Good on ya. Okay, got a question, Anne-Sophie. What does it say after H3O plus is? Is, for me, Mr. Weiss, also the concentration of H plus. H plus. All right, Anne-Sophie. So H3O plus is, for me, also the concentration of H plus. In other words, I look at it the same way. Okay. But on the AP, they'll ask for the H3O plus concentration. And I'm too lazy to do that a lot of the time. All righty. Ute. Got some conjugates. Life is good. Okay, let's go back to water for a sec, because it's important. 2/3 of our planet's covered with it. There's an awful lot of reactions that have to do with water. You know what an amphibian is, right? An amphibian can spend part of its life in the water and part of it on land. Well, what we got in chemistry is something that's amphiprotic. And that means the chemical can gain or, no, okay, let's make it in chemical terms. It can give or accept an H plus. And give or accept a proton, an H plus. So a lot of things are amphiprotic, but the most important one for you to know is water. Let's check out two reactions, okay? So here we go. Shaboom boom. H2O plus Br minus forms HBr plus OH minus. And the next one, H2O plus HI, the happy acid, or at least friendly, makes hydronium H3O plus I minus. So check it out. Look at this. Both of these I'm using water. But in the top one, we're going to say, aha, H2O acts as a what? And on the bottom, aha, 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 H2O acts as a what? You can't read that. So H2O acts as, that should be acts, ACTS. Okay, who can fill it in? All right, so let's do the top one. Check that out. Okay, so water is acting as a what? Acid or base? Look at what it's doing, not what it's becoming. What is it doing? So is it acting as a Bronsted-Lowry acid or base? I'm going to wait for a few answers here. Wow, everybody's correct, including Bella and Errol and Amina. It is. It's an acid. It's donating an H plus, and that's being picked up by the Br minus. So it's an acid here. Obviously, the other one's got to be a base. Let's see why that is. Well, it's a base. It's accepting an H plus. Oh, and therefore the other is acting as an acid. The H plus is being given by the I minus, and it's being accepted by the water. So that makes the water base under Bronsted-Lowry definition. Not wild. So even though it doesn't have an OH minus, it's acting as a base under this new definition. Okay? Yeah, good. Thank you. Thank you, everybody. We're cruising along good. Here's another amphiprotic one. Because we can. Okay, check this out. NH3 plus HCl. And now I'm going to do NH3 plus NO3 minus. Although that's kind of a crappy one. Let's not do NO3 minus. Let's do NO2 minus. Because that's actually real. Again, these are all aqueous, ladies and gentlemen. I'm just too lazy to put AQ every single flipping time. Okay? Cheryl will do that. Oh, no, she skips it sometimes too. I don't feel so bad. Okay? By the way, I'm looking at page 268, just so you know where I'm talking about. 268. That's where she talks about amphiprotic. But this is my example here. Okay. What will I make in the top one? See if you can guess. So can you fill in? Plus for number 1 and for number 2. So let's see if you can guess, huh? Try and do my acid-base reactions here. What will happen in the top one? Hint, with one chemical, you don't have any choice. The HCl, think of what it's got to do. And for the next one, you also don't have a choice if you think about it. It's got to go one way. Good, I've got one. Let's go ahead and get some other people typing in. Super, thank you. Yeah, looking good, people. Okay, that's got to be my acid. It's got to be. It can't accept another H+. It just can't. So it's going to be Cl- on the other side. Well, that means I got to take this and do what Amina and Anne-Sophie did. I got to make it into, oh, we know what that is. It's ammonium. Well, then we know it exists, don't we? It's ammonium. It's a common ion. That's how we get it. We take NH3 and throw another H+ on it. But now we're going to do the opposite. We're going to take it off, right? So the second one, let's see if somebody can fill in the blanks there. What's going to be for number 2? I'm going to pause and let you type. Please, everybody, try and do it so I know that lots and lots of you got it understood. So, like, obviously, this guy cannot deliver an H+. Therefore, what's it got to do? What am I going to get? Yeah, this one's a tiny bit harder, but really not much. Okay, Alex, you're 95% of the way there. Try it again, but figure out the charge. So part of this is guessing the charges on things. Let's try some other guesses. Yain, Amina, you could do that, but you're not going to lose both H+. That would be really difficult to have happen. Because once I lose one, it's really hard to pull off another one if it's already got a charge. So let's just have it, Amina, just lose one of the H's, okay? Just lose one H. Still waiting for somebody to really hit the nail on the head here. Okay, so who's going to do what here? Let's get some other of you to try out. All right, and Anne-Sophie, you're also 95% of the way there, but not 100. Or maybe you are 100. Did I figure it out? No, not quite. You're getting closer. You're getting closer, Amina. Let's do this one part. Okay, I think a lot of you figured out HNO2. If I add an H+, I'm going to get HNO2. All right, and I don't get any charge because I get an H+ and a minus makes 0. So it's HNO2, nitrous acid, and that's it. Now the tricky part comes here. I got to take an H+ off this, but it's not plus. So if I take an H+ off, what charge is left, gang? So I got to take a plus out of there. The only way to take a plus out of there is to leave what charge behind? Yes, Anne-Sophie has it now. Let's get some others in the X. So N H2 with what charge left behind? Thank you, Anthony. So it's going to be a minus left behind. I know that's a little weird. Back up, make sure you got it in your head. It's neutral. I can take a plus out of it, but then there's a minus left behind. How does that work? We'll go backwards. Minus plus a plus makes neutral. Neutral, take away a plus, minus is left. Okay? All right. You'll have more of those that you'll try when you do that section with Cheryl in the future. Huge. Okay. Acids are, any questions? Okay. Acids are electrolytes. Remember what that means? It means they give up something that has a charge, right? So, where do I want to go with this? I wish I had a demo, but I can't do it here. Let's imagine that we've got a circuit with a light bulb, kind of what Cheryl does too. And I want to have my light bulb light up. Well, the one way I can do it is I can send electricity. Here, it's plugged in over here. And I'm going to send it through a circuit that goes in a solution. And my solution has an acid in it. And let's make a couple of electrodes. Here's like pieces of carbon. And then my wire, so this is a wire, goes through the solution, out the other side, and back here, and then it will make the light bulb light if it's plugged in. Okay, that's a plug. So I'll say power source. So in other words, I got some positive and negative ions down here, okay? Plus, well, probably what, H plus, something minus. Let's call it like B minus, okay? H plus, B minus. And what those can do is those little guys can move. Remember how electrodes work. I hope you had this in chemistry. One's got to be minus, the other got to be plus. And so if I turn it on, the little H pluses will move towards this one. And the B minuses will move towards the B minuses will move towards the positive one. So they'll go like here. Here. So what electrolyte means is it conducts electricity. To make a short story long, okay? That's just a little thing I could do with a light bulb and a beaker with an acid solution in there. They conduct, singular, conduct electricity. But it's a big but, isn't it? Okay, they don't conduct electricity the same. Turns out strong acids conduct well. Weak acids conduct poorly. We're going to find out in a second why that is. Strong acids conduct well, weak acids conduct poorly. So imagine if this was a weak acid, it would be a really pathetic little light in my light bulb. If it was a strong acid like HCl, my light bulb would be, whoa, really lighting up, okay? I'd have a nice current flowing, and we'll see why that is in a moment, okay? So wimpy, weak acid, strong, strongly lit as a light bulb. And by the way, we need electrolytes in our body too. We talked about that, right? We need salts. There are also electrolytes if they are soluble. So we need soluble salts like table salt and stuff so we can have electricity go through our nervous systems, right? Which use electricity. So physics and chemistry, I love it. Well, it turns out that strong acids dissociate better. Dissociate. Now, we had that word, but it's been a while. Dissociate means to break up into ions, if you recall. And what that means for you and I is, okay, if it's more ions, then it's a better conductor. Duh, right? More ions equals a better conductor. Okay. Can somebody type in a strong acid that you know? Give me a strong acid, okay? What's a strong acid that you know? Because we need an example. Thank you, Antonin. HCl, perfect example. So if I got HCl and I dissolve it in water, so I'll say AQ because I want to emphasize that it's dissolved now. It's going to break into parts. Not surprising. It's going to break up into H plus ions plus Cl minus ions, and those suckers are all floating in the water. AQ. AQ, AQ. Well, that's fine. But because it's a strong one, I get lots of these. So let's change the arrows a little bit, okay? So maybe cross out your arrows. So really we get a lot of this happening. We get very little of these going backwards. So I'm going to get lots and lots of the products. I bet you know where I'm going, don't you? I'm going to have very little of this stuff left. It's mostly broken up H plus and Cl minus ions. Now, contrast that with a weak acid. So that would be a strong acid, okay? Strong acid. For a weak one, I don't know, man. Let's just take one that we did already. How about HNO2? Well, that one I get H pluses also. Plus NO2 minus nitrites, if you remember that one. And they're both floating in the water. You might say, well, that's the same thing. It's just different ions floating around. Here's the problem, or here's the difference. It doesn't happen much. What mostly happens is this stuff stays, HNO2, it stays in this molecule. So I got lots of this stuff. There, my friends, you have the difference between strong and weak acids. So this is a weak acid. It does not make a lot of ions, right? So I can't conduct electricity very well. This one does make a lot of ions. In fact, I drew them bigger, but I didn't have to. But I get a lot of ions for that. It conducts very well. And I see some of you knew some other acids as well. Good. HBr, H2SO4 is the other one. HNO3, dynamite. Glad you knew all. Those are all strong acids. Turns out, gang, there's only 6 strong acids. And you're going to memorize those 6, and all the rest are weak. Isn't that cool? If you know 6, you know all of them because you know which ones are strong. Therefore, you know all the rest are weak. I'll give you those 6 in a second. That's how. Okay. You ready? Put a little star by this guy. Only 6. So Bella, only 6 acids do this. Only 6 make strong acids, make lots and lots of ions. So only 6 acids are strong. And you guys already gave me some of them. You already know this. That's cool. So definitely HCl, the happy acid, HI, the not so happy acid, I don't know, HBr. Notice those are all halogens, HCl, HI, HBr. So you got H plus attached to 3 different negative halogen ions. And then H2SO4, the one Anne-Sophie was on her way to giving me. And the one from Amina and Bella was nitric acid. HNO3 is another strong one. And the only other one you may not know is HClO4, which is one we don't really use that often. It's called perchloric acid. Perchloric. Perchloric. But the rest we'll use over and over, okay? Nitric, sulfuric, hydrobromic, hydroiodic, hydrochloric. Those are all not so hard, but perchloric's kind of weird. Anyway, those are it. And then, Bella, you know that all the rest are weak and stay as the undissociated acid molecule a lot more. So all the rest are mainly this. These 6 are mainly their ion forms. Isn't that cool? So acids are pretty nice that way. Bases also, as it turns out. Well, you can guess where we're going, can't you? We're going back to an old friend, okay? And the old friend is called the K. So the equilibrium constant, KEQ, for strong acids. Remember when I did that with you? Okay. Bigger than 1, products favored. Less than 1, reactants favored. Which is it for strong acids, gang? Is it going to be bigger than 1 or less than 1 for strong acids? Yes, Anne-Sophie, we will. So the equilibrium constant will be bigger than 1, less than 1 for strong acids. Which way will it be? Bigger than 1. Thank you, Aiden. Exactly. Thank you, Alicia. Thank you, Amina. Yeah. So for EQ for strong acids is much bigger than 1. For weak acids, it's less than 1. Usually it's a lot less. But anyway, for the strong one, it's definitely way, way better than 1. Now, To be honest, we don't call it KEQ. We actually call it Ka. So it's the equilibrium constant for an acid. Is it the same thing? Yeah. Okay. Let's do a Ka expression. So let's do a Ka expression for HCl. So I got HCl goes to H plus Cl minus, and then the expression is Ka equals, is it same products over reactants? You betcha, same thing over and over again. So I got H plus concentration, which remembers the same as H3O plus concentration, times Cl minus concentration over concentration of HCl. Ta-da! And the number here would be really, really big. In fact, the number's so big, it's undefined. So all we can say here would be very large for HCl. How can I know those numbers? Look on page 277. And you'll see that the 6 strong ones, all they say is very large. There's not even a number. They're so big, right? So they're not like this. They're like, they're really big. Lots and lots of products, very little HCl left, okay? So there's an expression, and you can guess where we're going to go with the math. We can find out things and do all sorts of cool math with this, but that's kind of the idea. Another way you can write this, I'm going to give you the share away. Or you can say the Ka is equal to H plus, no, sorry, H3O plus times Cl minus divided by HCl. That's the way the Cheryl does it. Okay, I do the top way because it's easier, to be really blunt. Where is she getting this bottom way? What she's saying is this. She's saying the bottom way is from this. She's saying it's water plus HCl goes to H3O plus Cl minus. Now the water is liquid, so we don't include that in this Ka expression. That's why, pardon me, that's why it's just HCl at the bottom. So anyway, that's the share way. That's my way. Either way will serve you just fine. Either way will be okay with the AP people as well. Okay, another way to say this is this guy, I sometimes call it a Ka number, and it's actually called officially an acid ionization constant. Acid ionization. In other words, how much does it become an ion? Ionization constant. But you're going to hear me call it mostly a Ka number. And it's all on page 277. That's the Ka numbers for lots and lots and lots of acids. At any rate, 6 strong acids and all the rest in the universe are weak. So kind of nice to know. Okay, now, Anne Sophie is interested in me to talk about bases. So we're going to talk about your basic bases as well here, okay? All right, so let's do it. I'm going to erase this now. So I'm going to say bases. Yep. It's more or less the same kind of thing, or similar, okay? Let's do one, okay? Let's do an expression, and then let's do the KB for it. So the KB is called the base ionization constant. And it means how well does the base dissolve? If it's high, then it's a strong base, and so on. Okay, here we go. Let's do one. So as an example, let's take the one she did. Okay, so we'll take NH3 plus water, which is a liquid. And so it's going to be, we're going to grab an H plus off the water, because we want to make this a base, so it's got to accept an H plus, so I get NH4 plus. I know we did that one earlier. Plus, oh, look what's left, OH minus. That's why it's a base, because when I pull off an H plus from water, I get OH minus. Okay, and then the Kb expression, or base ionization constant, well, we still call this part the expression, is going to be these two guys, the concentration of the ammonium times the one that came from the water, the OH minus, divided by the concentration of our base to start with, NH3. Notice, again, the water doesn't go in there because it's a liquid. Liquids don't go into equilibrium constant expressions. So that, folks, is it. I don't know if she has any KB numbers or not. I'm looking. I don't think she has any. You'll have to get some KBs. Can I give you kind of a cool little tip, though? Here's a cool tip. A Ka and a Kb are very much related for an acid. So if I take a Ka times a Kb, it equals this magic number, 1 times 10 to the negative 14. No, is that right? Let me just think a sec. Yeah. So that's pretty strong. So it's basically pretty weak. Yeah, I think that's right. Okay, so if you got the Ka, you can always get the Kb and vice versa. All right? I hope that's right. Maybe I shouldn't do this now, but I've already written it. Let me take a quick look. I'm 99% of the way thinking this is correct, but I don't want to screw you up. Yeah, Yo, yeah, that's right. That's right. Okay, sorry. Yeah, that's correct. Okay, we need to talk about water. So I'm going to kind of see if you got any questions here. But let's make a general thing, okay? All right. Generally, an acid, or I can say acids with strong, well, okay. I didn't really say that very well. Okay, but I can write it that way. Acids with a strong conjugate acid, kind of repetitive, have, I don't need a comma there. Acids with strong conjugate acids have weak conjugate bases. And vice versa. Let me write it shorter for bases, okay? Bases in blue. Weak bases, no. Let's make it strong bases. Strong bases have weak conjugate acids. This sounds really confusing, but I'm going to give you an easy way to understand it, okay? All right. Okay. So strong bases have weak conjugate acids. Strong acids have weak conjugate bases. Let's take a strong acid. Let's take HBr. So if I have that thing broken up, I got H plus Br minus. Well, so that's strong. So the Br minus is really weak. It doesn't really do much. It doesn't act like a base much. It does not actually pull off and take from somebody. It doesn't accept an H plus very well. It doesn't go backwards much. Now let's do one that's even more familiar to you. Check this one out. HNO3. So H plus NO3 minus. Well, this is a weak base. And this, I know, of course, a very strong acid. That's HNO3 is one of the strongest ones. But check this out. Remember, NO3 minus is one of those spectator ions that doesn't do much most of the time. Now you know why. It's the weak base from a strong acid. So the acid does a lot, but the NO3 minus doesn't do squat. So therefore, it's a spectator ion. Ha ha! Okay, let's talk about the bases, and it's going to be the same story all over again. First, let's talk about the strong bases. I always learned there were 6, okay? So strong bases are basically OH minus attached to this family or this family. Remember the alkali metals or the alkaline earths. But a lot of these really don't happen much. So really, I'm just going to say strong bases are going to be LiOH. I'm going to keep going. Na, pardon me, NaOH, sodium hydroxide, KOH. And you might say, well, Mr. Weiss, what about rubidium hydroxide? You know how much rubidium we got on Earth? About enough to fill up half a shoe. So don't worry about rubidium or cesium or francium. We just don't have much. Okay? But we got some in the second family. Magnesium, okay. Cheryl says, yeah, to magnesium. I don't know. What did she say about magnesium? I was just looking at it. She says, even though it's slightly soluble in water, which means it breaks up a bit, the amount that does dissolve completely ionizes. A very common weak base in water is ammonia. Other weak bases, blah, 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 blah. So I don't know if she's including it. I don't think I usually do. So I'm going to say the 6 of these are going to be CaOH2, strontium hydroxide, and your friend and mine, barium hydroxide. All right. What about radium? Well, we don't have a lot of that. Don't worry about it. So really it's 3 here and 3 here. Okay. So if you know these 6, you're pretty good. And again, MgOH2, I don't know what she wants you to do with it. I don't think it's particularly strong. Could you shift the camera down? Oh, sorry. Thank you, Bella. That's what I get for talking the whole time, huh? Okay, so there we go. So the strongs are, let me read them off. LiOH, NaOH, KOH, CaOH2, SrOH2, BaOH2. So from the first and second family, or groups, we could say, with OH minus. Okay. Now, let's take one of these. Ready? Let's take NaOH. So I have it ionized. I get Na plus OH minus. Well, we know that's strong. So you know what? It's a strong base. So the conjugate acid, the Na plus, is weak. Strong base. So wait a minute. Am I saying that right? Hold on. So Na plus, so that's a strong base. The acid's going to accept an H plus, but that's not really true. Forget it. I got to think about it. But anyway, I want you to circle this and write, aha! This one is also a spectator ion. Why? Because like the NO3 minus, it doesn't do anything. The other one does something. The H plus does it here. Here the OH minus does something. So the Na plus is another spectator. In fact, these are mostly spectators. Look at this. Li plus is a spectator. K plus is a spectator. These are not spectators all the time, but some of the time. At any rate, but the first family definitely is, right? So that kind of explains why we get those spectators that do nothing, because they're attached to somebody who does something. In this case, a strong base. In this case, a strong acid. Yeah? Spectator, spectator, nothing, nothing. H plus does a lot, OH minus does a lot. Okay. So to make a really obvious thing, so if the Ka is is going to be a big number. The Kb is small. And vice versa. If Kb is big, the Ka is small. Makes sense, right? Makes sense. Because its conjugate is small, is weak, if this is big. If the base conjugate is big, if the base is big, its Kb number, then the conjugate is going to be some kind of puny small number. All right. That's less blurry. A little less blurry for you, I hope so. Here's something kind of cool. How we doing? We're doing okay. Page 279. This I'm telling you because it's kind of cool. I'm not sure it's all that useful, but it's kind of neat. Check this out. If I got HF, then the difference between the atoms, here's the H, here's the F. The distance between the two nuclei is 92 picometers. Don't even ask me how small that is. Tiny. Whereas HCl, she's got a bunch of them, but let's just look at two of them. HCl, it's a lot more picometers. It's 127. So why is this weak? And why is this strong? Okay, hint, I've got an attraction between the two atoms, probably a plus and a minus, right? H plus, F minus, H plus, F minus. Look at the distance. What does it mean if it's further between the two nuclei? What does it tell you about the bond for HCl versus HF? Let me ask my question more exactly, because you're probably wondering what I want you to type. I got a bigger distance here. Maybe I can make that more clear. Sloppy drawing. I want that to be clearly bigger. Okay? If that's a bigger distance between the two nuclei, will that be stronger or weaker if they're further apart? These are closer together. Will that be stronger or weaker, the bond? So let's take HCl. They're further apart, the two nuclei. Will that make the bond stronger or weaker if they're further apart? I'll keep my finger here until you have a chance to write. These are further apart. Will it make the bond stronger or weaker if the nuclei are further apart? Think about it. Good. Let's wait for a couple more answers to pop up. The further apart, stronger or weaker bond? Thank you. Good. Yeah. Thank you, Louisa. Thank you, Alex. Thank you, Penelope. You're all right. It's weaker. Let's write it over here. So strong acids have, ironically, weaker bonds. That's why they fall apart so easy. Oh, yeah, right? Now, it's not always this reason, but here the reason is the distance between the nuclei is just big, so it's weaker. But the cool thing is that strong acids have weak bonds. And look at the opposite, HF. Weak acids, why are they weak? Why do they not break up much? Because their bonds are strong. So they don't break up. Or they don't ionize much. Ooh, let's use a nice scientific word. Doesn't that make total sense? So if they really stick together, of course they don't ionize because their bonds are strong. Strong bonds, weak acid. Only the ones that have really weak bonds are strong acids, like HCl. Kind of cool, huh? It's almost like chemistry makes sense. Let's see if you got any questions about that. All right, I want to show you one thing that she tells you about, so you probably ought to know. Those of you that had me might remember this. We're talking page 280. She talks about carboxylic acids. They got carbon in them. And you might say, well, duh. Well, there's something weird I got to show you. And it's this. Is it a hexagon? Yes, but that's not what it represents. A hexagon in chemistry is called a benzene ring. Some of you might have had that with me years ago. And what it is, it's 6 carbons, C6, and that each little carbon is an H that's usually not written in. So it's C6H6. So I want you to know what a benzene ring is because she assumes you know that. Okay. Usually they don't write the H's, but they're there. So that's a benzene ring. Is it important? Not really. Did she show it to you? Yeah. So I guess I figured I better tell you what she's doing. Okay. Ute. Ute. Let's mark that. I'm going to stop right there. Any questions from you? Good. We're up through section 5.2, and we're going to stop right there today. And work hard on the chapters. I know it's hard because you guys are out there all on your own. If you get stuck on a problem, write me, okay? And I will try and help you. I'm not perfect, but I'll do what I can and give you some strategy, okay? All right. Okay. Be well, everybody. We'll see you on Monday, and I'll make up a AP Classroom quiz on Chapter 1, reaction rate order, and get that ready for you. Okay. Bye-bye. Like the Corona haircut? Nice, huh? Bye.